morning. In the last class we talked of electrostatic forces, namely we said charge into the voltage gradient, which was the electrostatic or the electrical field, and we also said we could have a charge moving in a magnetic field cross B is the net force what we get in a charge. This was what we called as Lorentz equation. B is the magnetic field in Tesla, E is the electrical field in voltage per meter, and charge is in coulombs, and force is also a vector. We continued with this and we found that the force what we could get in the case of the electrical field could be written as the current into something like 2 into something divided by Q into the mass into the voltage, right. And how did we get this? We got something like the potential difference voltage was equal to the work done per unit charge, and therefore we were able to write QV over here, and from this relation and also from the relation force is equal to m dot into Vj is what we got this particular relation. And this force is in newtons, I is in amperes, voltage, mass, and the charge over here. We found that it is essential for the mass which we are charging to a level of Q coulombs should be substantial so that we get some force, and we said electrons which weigh something like 1 over 1837 or 1838, 1837 we will say, 1 over this is the mass of an electron. That means if a proton weighs 1 kilogram or 1 unit, the mass of an electron is something like 1 over 2000 of a proton, and therefore it is very difficult to have electrons which will give sufficient force, and normally positive charges are used for generating the forces, and we cannot use the electrons because their mass is so small that I do not get any impulse at all. Therefore these positive charges are what are called as ions, and therefore such mechanism of using the electrostatics, namely an electrical field for generating a force, is also known as ion propulsion. At this point in time I will also tell you we call it as an ion rocket, but the type of forces which are generated are so small that instead of calling it as ion rocket we call it as ion which generates some thrust or ion thruster. Therefore when we talk of low thrust rockets we call it as a thruster instead of a rocket, but anyway you could call it as an ion rocket. It depends on the person who uses it. There is no very hard and fast rule that it must be called as a thruster and not a rocket or stuff like that, but generally you find the low value of thrust when a rocket produces, it is known as a thruster, and all the electrical rockets like electrostatic rockets generate low thrust, we call it as a ion thruster. Having said that, we also went one step further and said if I have to use this electrostatic principle and generate an ion rocket, now I call it as an ion rocket because I know I am going to use positive charges, and we said yes, we would also like to have substances whose molecular mass is larger or whose atomic mass is larger, and therefore I rather have heavy substances like maybe mercury, maybe cesium, maybe xenon. Mercury we said is something which contaminates the surfaces of spacecraft, because what happens in a spacecraft, if I consider, let us say I just put it down here, I consider a spacecraft, it consists of lot of sensors, maybe an earth sensor, maybe a sun sensor, and these sensors are all glass type of things. It consists of optical quality glass which gets the radiation from the earth, and therefore an earth sensor, and if mercury is let off from the spacecraft it will go and form a monolayer on it and it will make it opaque, and therefore mercury sort of contaminates, and therefore mercury is generally not used. It was used in the earlier spacecrafts and is no longer used. Maybe cesium was also used but no longer used because it is a reactive metal, and something which is universally used today is xenon, which is a noble gas. Therefore how will a construction of an electrostatic rocket look like? Well, I need to pump in this particular xenon gas, I need to generate positive ions of xenon, and then maybe I put something like a negative grid over here, something like a screen which is negative, such that it will attract the positive ions towards it, and again I put another screen over here which is still more negative. That means I have a voltage difference between these two. This is less negative than this, that means it is positive compared to this, and therefore whatever xenon ion is being attracted by this from this source, because I am generating the xenon ions here, I want it to extract, therefore I call it as an extractor grid. It extracts all the positive things, it attracts and brings it here. This is still more negative, and therefore what happens is, because I have some negative space here, or rather I have a field here, electrical field between this and this, it is pulled here and it is accelerated, and out goes the ions, that is xenon ions, at a high velocity Vj, and therefore this will be the construction of a ion rocket or ion thruster. Therefore now if I were to put a thing here, well, I put a negative value of charge here, I put a battery here, a high voltage here, maybe this is my positive, this is my negative, I connect it here, maybe I connect another one here with respect to, if I am going to have a grid which is passing this, and this grid generates the positive ions. I will come back to this generation in a moment. Well, this is going to be negative here, this is going to be positive, negative here, and therefore this attracts, and this thing which is still highly negative is what is known as an acceleration grid. See, I have assumed that xenon positive ions are created here, and how do you create the positive ions? See, you all grew up in a generation wherein we did not have these vacuum tubes. You all grew in a generation with semiconductors and all that. Previously we did not have these semiconductor tubes, and we had what were known as vacuum tubes, which consisted of diodes, triodes and all that. And what was done in those cases? We had something like a filament, preferably of tungsten, which used to generate, when I heat the tungsten, the work function of tungsten is low, so that when it is heated it could create electrons, that means something like negative charges. Therefore if I could have a grid made of tungsten or even molybdenum for that matter, and I heat this particular grid, maybe electrons are generated from this grid, and these negative ions, when they hit against the flow of xenon gas which I am passing through this over here, the xenon ion, neutral xenon ion, is hit by a negative charge, and this fellow knocks off one more electron over here, makes the xenon positive, and this is how I could create it using a sort of a resistor which is heated, which I call as something like thermionic emission. It is not only thermionic, but whenever I have a gas which is flowing and I generate some ions, therefore whenever I am creating, I am knocking off one electron, that electron is also available, and in this space I have lot of these electrons which are going to hit the xenon more and more, and therefore I have something like a field emission. In this particular field I keep on generating more and more ions. Therefore at this point in time I can tell myself, well, by having a grid which is a low work function material, and work function material low means I could use tungsten, I could use molybdenum, well, I could also use the alkali metals. Alkali metals are metals such as calcium, and these also have a property, we call it as a work function property, such that when it is heated it releases the electrons, and therefore I release electrons, it interacts with the neutral flow of a xenon gas, creates positive ions, and by field emission the xenon ions grow, and therefore this is being attracted by an accelerated grid, and this is what gives me the thrust. Therefore I have something like a grid to generate ions, a grid which is extracting the ions from this flow over here, because I would like to attract the ions more and more, and once it is attracted the accelerated grid further pushes it at a high velocity Vj, and therefore such type of construction is known as gridded. I have as 3 grids, gridded ion thruster. This was started by a person known as Kaufman, and therefore it is also known as Kaufman thruster. This ion thruster has been used in several missions starting from even mid 70s, and in fact in India we used one particular satellite known as Application Technology Satellite made in USA by Hughes Corporation, ATS-6. This was used as an experiment before we got into INSAT for maybe communication purposes and all that. We needed to do an experiment because in India most people were in villages and we never knew whether a satellite like INSAT would be useful. Therefore in the period 1975 to 1980 or so, we got a satellite on loan from US which is known as ATS-6. It beamed programs for the villages, different villages in the country, and that was when we saw, well, the INSAT satellite would be useful in improving, let us say, the education in villages, maybe the healthcare in villages. And we had very backward villages like in MP, places like Jabua, wherein they were all tribals, and we put some power sources, demonstrated that a satellite will be useful in improving the quality of life, and in this particular satellite they also demonstrated ion propulsion or ion thruster. Therefore we see, yes, a gridded ion thruster can be used, but is this the only method of generating ions? See, after all, I need to generate ions. To generate ions, it is also possible that in substances like xenon, in which I can easily knock out an electron out of it and make the xenon to be positive. That means I remove something, it net becomes positive. I can use something like a low pressure xenon, low pressure gas, and into this low pressure gas, supposing I were to heat the gas. And how do I heat the gas? I sort of oscillate something, like I put radio frequencies in it. I have a volume of gas, I put radio frequency into it, I sort of excite the gas and heat it, and in that case when I heat it, gases like xenon tend to form maybe positive and electrons negative, and I use the same attractive forces and do this. In other words, I use radio frequencies also to generate positive charges, and if I use radio frequency, well, the thruster is known as radio frequency ion thruster. Maybe I will write it here. Or it is known as RIT. It has also been flown. Therefore we are talking of some of these electrostatic type of mechanisms wherein I could use gridded ion thruster, maybe radio frequency ion thruster, or even I could think of some other configurations. In fact, you have this rocket pioneer by name Yuri Kondratyuk, who developed something known as a colloidal thruster, which again works on the electrostatic principle. Here you have a colloidal. What is a colloid? You could have something like, let us say, fine droplets which are scattered or something. These fine particles of dust or droplets, which is something like an aerosol, are charged, and these charged particles, if in an electrical field, could be accelerated, and this could be used to provide thrust. Namely, you charge the colloidals, and these colloid particles, once they are charged, you put it in an electrostatic field and you generate thrust, and this is what is known as a colloidal thruster. Using the electrical field as it were, if I can generate charge in a particulate, I can accelerate it and I can get a particular thrust. Well, this is all about electrostatic, but I think having studied it, let us see, are there any specific problems in this? Is it something which is so readily usable, and are there some improvements in it? Because we do not see ion propulsion being used as much as some other forms of electrical propulsion, and the reason being, maybe what is happening, let's see what are the problems. You are having these accelerated charges, accelerated ions hitting against this particular grid, which is something like a sieve, something like an open thing over here, a sieve over here, and when these things are hitting against it, it gets sort of, it removes the metal, and this is known as sputtering. That means I pass high velocity charges. High velocity charges, when it impacts here, it corrodes the metal, and it is known as sputtering. I think we must remember this word sputtering, because when we talk of nanomaterials, one way of making nanomaterials is, I take a material, I allow high velocity charges to come on it, I generate particulates which are very fine particulates, which are nanoparticles. Therefore, the sputtering sort of erodes the thruster, and the lifetime of the thruster reduces. Therefore, one problem I can immediately say is a problem of sputtering. But how do you correct for sputtering? Maybe I can only reduce it. I use something like, instead of using tungsten, if I use molybdenum, it is less susceptible to sputter, and therefore I use something like a molybdenum grid. There is a second problem, and this second problem is common to almost all types of electrical thrusters. Let's see this problem. Supposing, let's say I have this particular container now. I now put the thruster like this. I allow the charge to come over here, and now I create the charge over here, xenon positive. I put a extraction grid over here to get that thing out, and at the end of it I put the acceleration grid, and we said maybe the voltage of this could be something like 1.5 kV with respect to 0 here, and this could be negative with respect to this by some, let's say, a few hundred volts. Now what is going to happen? The positive ions are going out, being accelerated at high velocity. All the electrons are getting accumulated within, that is somehow here. And how are positive ions getting generated? You are removing electrons from it, you are removing the positive charges from it, therefore the thruster becomes negatively charged. Because what is it we are doing? In this system, I'm getting the positive charges out, the thing becomes more and more negative, it becomes negatively charged, and therefore when it becomes negatively charged, even though I am pushing it out, there is a tendency for these things to get retarded, pull back as it were, and therefore if I leave the charge like this, the negative charges will decelerate and cause it to come, and therefore it is necessary for me, before I push it out, to be able to neutralize the positive charge. And how do I neutralize the charge? All what I do is I put another cathode, or a cathode is something which generates negative ions, which means I put another, say, some thermionic emitter over here, and I generate negative charges, put it into this such that it will hit this, and what comes out is neutral charges, not positive charges but neutral. Therefore the second problem, which is common not only for graded thruster but any thruster, is we need to neutralize, that is neutralization must be done. Therefore an ion thruster should have neutralization of the charges, otherwise when negative charges build up, it will not be able to push this aside. Well, there is a third problem. The third problem, let's see on this figure how we can visualize this problem. What is it we are doing? We are pushing the charges, positive charges, accelerating it over here. When the positive charges move like this, I have something like a current which travels in this direction. What is current? Current is the motion of electrons. Therefore I have something like a beam current. What is a beam? I have this as a beam current as it were. Let's put it down properly. I have a beam current. As the positive charges are moving, I have a beam current in this particular direction. And what will this beam current do? Between the accelerator grid and this particular acceleration grid and this extractor grid, even though this is negative, this beam current will reduce the effective voltage with which it is getting attracted. Maybe for a critical value of beam current, no more extraction is possible and the thruster will fail. That means there is a maximum value to the beam current. And we will not go into too much details of this, but we recognize, yes, there is a maximum amount by which I can push it out, because as I go, more and more of the positive charges are moving out, I get a current in the opposite direction. That current will ensure that I do not have sufficient negative voltage to suck in or extract the positive charges here, and therefore there is a threshold value of this, and this maximum beam current is given by the current density J, which is equal to beam current divided by the area of cross section, and this is given by a law known as Child's law, Child-Langmuir. It is very easy to derive this law, Child-Langmuir law, which says that the maximum value of current density which stops further getting all these things here is given by 4. You remember we talked in terms of permittivity of free space divided by 4 E0 by 9 into 2Q by M into the voltage to the power 3 by 2 divided by L square. In other words, all what I am saying is there is a limiting value of beam current beyond which it is difficult to extract the ions over here and the thruster will fail. Therefore, the maximum value of current which is possible in an ion rocket is now given by I is equal to JA, or J is the critical value, let us say. Therefore, the maximum current what I can get in an ion rocket is equal to A into 4 times the value of permittivity of free space divided by 9, unit of permittivity we saw as farads per meter, into 2Q divided by mass of the charge into voltage to the power 3 by 2 divided by L square. But I already know the force equation, and the force equation or the thrust developed by a particular ion rocket we derived as I into under root, what was it, 2 Vm divided by Q, and therefore the maximum thrust which an ion rocket can develop, I substitute the value of A here, I get 4 permittivity divided by 9, 2Q by M, and therefore this becomes 8 over here, because I have 2 coming here, 8 E0 by 9, and Q by M and Q by M cancels off, voltage to the power 3 by 2 is equal to V to the power square divided by L square into the value of A, which is the maximum thrust which is possible. How did I get it? A comes over here, 2 and 2 gives me 8 here, 8, permittivity of free space epsilon naught, 9 over here, and I get V, the balance V which is left here, V squared by L square. And in practice, and this is the equation to the maximum thrust which can be developed by a ion thruster, and we find that normally the thrust is around, let us say 10 Newton to something like 10 millinewton, very low thrusts are generally derived, 10 millinewton to something like 200 millinewton. The maximum specific impulse, or rather we put it in terms of Vj, is around 24,000 meters per second. When we talked of chemical rockets, we found that the Vj is around 3000 or something. The ion rocket gives around 10 times the performance, but at the reduced thrust levels. And what is the maximum thrust level? Given by this particular equation. Well, this is all about ion thrusters, maybe what we called as maybe radio frequency ion thrusters, and these are what is being used for. It has been flown in several missions and it is a strong contender. In India also we are developing the ion thrusters, but something which took the community by storm, or something which is totally different, was looking at the problem in a slightly different way by the Russians. I think we must try to appreciate some points. See, all what we are saying is, we have the Child's law, which I just now wrote, saying that there is a limitation on the amount of charges which can be emitted and the thrust which can be generated by the ion rocket. Now, there is a principle in electrical engineering or in physics known as Hall principle. What does this principle tell? Supposing I have a conductor. In the conductor I pass a particular current I, and this conductor is placed in a magnetic field which is perpendicular to it. That means I have so much Tesla normal to the current flow in amperes. Then the Hall principle states that when a conductor carrying a current is placed normal to a magnetic field, a voltage is generated normal to both the current and the field. In other words, if I pass a current like this which is in a field B, I generate a voltage normal to both, and this is known as Hall principle, or something known as Hall effect. In other words, what is it I am telling? Can we make use of this? In other words, I am always passing current, I am having charges, I am passing current over here. If I were to put another magnetic field, I could have something like a voltage generated, and this was used by, as I said, by the Russians in the following way. Let's try to see whether I can use this principle in improving the performance of my ion thruster, because as I said, in an ion thruster the thrust is small, Vj is excellent, and I need a good field, and therefore I use a voltage of around 1.5 to 2 kV to be able to attract it. And since my distance length has to be small, my distance between the extracting grid and the acceleration grid is something like 0.5 mm. Therefore, without sparking, without doing this, it's not easy business. That means I am talking in terms of dimensions. Let's try to take a grid thing like this, and I have an extractor grid, I have an acceleration grid. This is around 0.5 mm. The voltage across is something like 1.5 kilovolts, and therefore construction is quite difficult. Therefore, what is done over here? What they thought is, if I were to have something like this over here, maybe I put something like a annulus here, and let's just consider what is it I am talking of. I am talking of something like a cylinder over here, and I am talking of a annular gap between the inner and outer, and supposing I were to put a magnetic field in this annulus, I just put a magnetic field, some Tesla in it, okay. That means in the annulus between the inner and outer I have a magnetic field. That means the magnetic field could be, let's say, in this direction over here. In other words, let me take a section over here, a section over here. In this I put a magnet here, I put a magnet here, therefore I have a magnetic field in the radial direction. And now I put, let's say, an anode here. That means I sort of put something which is positive voltage here, and here I put a cathode over here, and the cathode, when I heat it, generates electrons. Because I heat the cathode, work function is small, it generates electrons. The positive one is going to attract it in this direction, through the annulus it will go, and therefore electrons are moving in this particular direction, and the magnetic field is in this direction. Therefore, now I get a tangential, that means normal to it I get a voltage, and therefore the electrons, instead of moving normal, will now move in a path which is spiraling here. When the electrons are spiraling here, what I do is, through this I admit the xenon gas over here, and the xenon gas, when it comes into the spiraling electrons, is going to collide and generate positive charges, and these positive charges will be pushed by this positive, and I get a net flow of xenon positive ions being pushed by positive, and this gives me the thrust. Therefore, I use Hall effect effectively to improve my performance of the ion thruster, and this is known as Hall effect thruster. These thrusters have been flown by the Russians in several missions, Molniya missions, they say Cosmos rocket and all that for their satellites, and this has been widely used, and in India also we are working on these satellites. It was supposed to be flown in the last GSLV, but as you know, the last GSLV did not really fly because it had some problems in the earlier part of its mission, but people are working on it. Therefore, all what we will say is Hall effect thrusters make use of the spiraling effect of the electrons which essentially collide, and since the spiraling effect is used, you do not have things like Child's law saying that beam current is there. This is essentially a plasma consisting of lot of neutral gases. You do not have the problem of any sputtering here, and it is a easy thing in which I can use it, and I use a low voltage of around 300 kV, 300 volts I am sorry, and there is no question of a gap, and the thrust, the Vj what I get is somewhat lower, of the order of let us say 16,000 compared to 24,000 what I get, maybe let us say 12,000 to 16,000 meters per second. But even though I get a smaller value, I use much lower voltages, and this is what is known as a Hall effect thruster. It is also spoken of as you are creating a plasma which is in the annular passage stationary. Therefore, you have stationary plasma thruster, and more often than not it is referred to as stationary plasma thruster, and this is what we make use of the Hall effect in this. Therefore, we have talked in terms of the electrostatic principle, and in the electrostatic principle we talked of ion rockets, maybe radio frequency ion rockets, stationary plasma thruster, maybe we could have a colloidal thruster, and these are all what comes out of this principle. Let us go back to the next part of it, namely the electromagnetic principle. In the electromagnetic principle things were small, and whenever we are studying all this we are not looking at the description of a thruster, but we are looking at the operation mechanism so that we can go ahead and work out some numbers and also design one. And therefore, we said, well, a force can also be generated in a magnetic field when a charge moves at a value of velocity. This is the force which is generated, which we call as a Lorentz equation. Therefore, now I say, yes, I have maybe an electrical field, let us say, which goes into the board over here, and in this maybe I pass a charge q. We still say yes, a positive charge is better because electrons do not have much of mass and much of the force which is coming. I have a charge which is going with a velocity v, and therefore if this is going in this, this is going in this, well, maybe I should get a force in this particular direction. Let us calculate the magnitude of the force from this particular equation. We have force is equal to q into the velocity. Well, let us say I have a distance d over the field over here, and let us say I am interested in velocity, therefore velocity I can write as d by time taken for the body to experience a force in this particular direction, or rather let me say I move it in this particular direction such that I get a force in this particular direction. Therefore, I say d by t is my velocity, and force I say the magnitude of the force, I say the value of the flux in Tesla is let us say b naught. I just use a word because I want to differentiate the vector from the scalar quantity Tesla over here. Therefore, I have q, which is the charge, and this is the time over which it moves in the electrical field, d by t in b naught, and therefore q by t is current. I can also write it as current into d into b naught, and this is my force. Therefore, I find in a magnetic field, if I have a current I and the depth of the magnetic field is d, I get a force F over here. And to be able to complete this scenario, if I were to write maybe the force as equal to mass into acceleration, where m is the mass of the charge, I get m into dv by dt is equal to id b0, where b0 is the magnetic field, or rather I get dv by dt is equal to id b0 by m, or since at the initial state v is equal to v0 at time t is equal to 0, I can straight away integrate v is equal to id the into t, or rather the value of x at t, again x is 0 when I have no at t is equal to 0, I get id b0 t squared by 2m. I can go ahead and then simplify the, if I want the velocity here, I can substitute t square, I can take the value of t from this, t is equal to therefore under root of 2m into x at the time t divided by, or just I say x at time t divided by id b0, and therefore I can get the value of velocity which is required over here to give me the particular force. And these are the only set of equations which are applicable for, let us say, a thruster which will make use of a magnetic principle. But in case of a magnetic principle, what happens? You must have the charge must be given a velocity. What is the difference between electrostatic and electromagnetic? In the other case, I just have a charge which is accelerated by the field E, and what was the acceleration? V is the voltage between the acceleration grid and the extractor grid, the distance between them is this, the value of the field is E divided by L. Whereas in the case of a magnetic or electromagnetic thruster, I have a field which is available, and into this field I have to move the charge with a given velocity. In other words, I am talking of a dynamic situation, and therefore electromagnetic thrusters or magnetic rockets are known as dynamic thrusters, because you need to have a velocity to begin with, and therefore if I have a plasma, it is known as plasma dynamic thruster. But most of the plasma is in a magnetic field, it is known as magnetoplasma dynamic thruster or MPD. These are about the magnetic rockets. And let us take a sketch of it. We now know the principle, let us take a sketch of how it must be. Well, I could have a magnetic field in a tangential direction. Maybe I could have in the orthogonal direction a current I, and therefore I will have a thrust normal to it, which is my force. Let us see the construction of it. Well, I have a chamber which comes like this, maybe I pass my gas or my charge into this. I have a construction like this, maybe I put a material over here, maybe I have an magnetic field in this particular direction. I charge the flow over here, this is my body over here, let us say. I put, let us say, voltage here, I put a voltage here such that I make the charge go in this particular direction or the current flow in this particular direction, and now I get a force in this particular direction. And this is how a magnetic electromagnetic thruster operates, which we say is a dynamic thruster, or we say magnetoplasma dynamic, because you have a plasma of current which is there, current goes in the radial direction, and therefore the force you get in this particular direction. Well, these are about this, one development which maybe Kanpur people, IIT Kanpur is working on, is something known as, instead of having the thruster in this particular direction, why not you have something like a material like Teflon, and I put an electrical spark here and therefore generate a plasma. When I have some material like, let us say, Teflon, which is essentially carbon, fluorine and all that, I generate carbon charges, I generate fluorine charges, and these fluorine charges in a field whenever I put a spark, I generate little bit of this, and this gets into the magnetic field here and it generates a thruster. That means I generate thruster in pulses. Whenever I put a spark, I generate these ions and I generate pulses. These are known as pulsed plasma thruster. See, you can keep on evolving, and that is the beauty of propulsion. And in propulsion, all what you want is some field to generate a force. You use different types. In pulses you generate, as a steady flow you generate, and these are the different possibilities. These things have been done elsewhere, and it has also been flown by the French people in one of their NOVA satellites. Well, I think it's time to take stock of whatever we have learned so far in electrical propulsion. We tell, yes, it could be either electrostatic or it could be electromagnetic, and in electrostatic we had the ion rockets, we had Hall thruster, stationary plasma thruster, we had the dynamic. Therefore, let us quickly go through it and see how we conclude the question on thrusters. Well, this is what I said, you need an acceleration grid, you need a neutralizer in which I put the electrons into it such that what comes out is neutral, and these things are not taken back over here. One, this is how an ion rocket looks like. I admit the xenon gas over here. This is the chamber in which I make the positive ions, and this is something like an extractor grid, this is something like an acceleration grid. The spacing between them is around half an mm, and the voltage is around 1.5 kVA. That means I have an intense field, the whole thing is accelerated, and I put something here in which I inject the electrons into it for neutralization. Therefore, I have magnets, and why do I put magnets in this case? To make sure that I have a controlled plasma here. Mind you, it's not something like an electromagnetic thruster. Therefore, these are the constituents of a ion rocket or ion thruster. Well, we talked in terms of thermionic emission or bombardment of ion thruster, because I bombard the neutrons onto the the electrons onto the charges, and by bombardment I get ions over here, and this is what we had, the gridded ion thruster, also known as Kaufman thruster. I could have field emission wherein bombardment takes place and secondary electron emission also constitutes to generate more current or more charges, positive charges. We talked in terms of radio frequency thruster. I talked in terms of some substances which could be charged, like a water droplets or some colloids which could be charged, and I could generate a thrust. Well, this is all what we say is, as current density increases, we had the three problems. Maybe the extracting voltage becomes less, therefore the Child's law came into the picture. We have limitation on beam current, and we found out how to get the maximum value of thrust. And as I said, these grid thrusters, even though there are limitations, it was used for the Indian INSAT, which we had used a satellite known as application technology satellite. It has been used in some missions like deep space, which leaves our solar system and gets into distant space. And the thing is that to prevent sputtering, we use molybdenum in ion rockets. But considering the space charge limitations, the tendency is to make use of the Hall effect, wherein you allow the electrons to be attracted over here, the electron spiral generate the positive charges, repelled by the positive charges, and out it goes over here. But I did not really specifically tell about disadvantages of the Hall thruster, but let us look at the construction. This is the center line. I put magnet here, this is the annulus, I put a set of magnets here, I have a strong magnetic field. The strength of the magnetic field in the Hall thruster, since we talk of numbers, I think we should have some numbers for the field. We told that the Earth's magnetic field is around 0.4 into 10 to the power minus 4 Tesla. Compared to that, it's around 0.1 to 0.3 Tesla is what is the strength of the magnetic field which is used in the Hall effect thrusters. As I said, voltage is around 300 volts, and you can generate slightly higher thrust compared to the ion rocket, but as we said, the Vj is less than what you get in the ion rocket, right, ion thruster. But there is one problem which we can immediately foresee. You have the anode, you are positive, it is pushing out the charges with some velocity, and therefore the velocity being lower, it does not really go as a free stream, it tends to diverge a little bit, and when it diverges, it goes and contaminates the other bodies, spacecraft around it, and to be able to prevent it, people talk in terms of something, can I reduce the length over here such that the positive charge is more effective, and that is what I also show here after a couple of slides over here. Let's take a look at it. Well, this is the picture of a Hall effect thruster. This is where the electrons are generated using a cathode. It enters the annular gap over here. There is a strong magnetic field in this particular gap over here, and therefore the electron spiral. You have an anode here which pushes the thing out, and you get the thrust over here. This is the phase view. In the annular gap, through this the xenon comes out and you get the thrust. This is the sort of the cathode which generates the electrons. To prevent the divergence which leads to contamination, a small length is to be preferred, and this small length thruster is known as the anode layer thruster, or rather TAL. Well, we have considered this. I said 0.1, the field is around 0.04 Tesla, voltage around 300 volts, we get around 15,000 meters per second, and we said since the electrons are just spiraling, they do not contribute to thrust, the efficiency is low, around 70%. Well, we considered the electromagnetic thrusters, and this is an electromagnetic thruster. Well, you have a tangential field into which charge comes over here. I have a voltage difference between this and this, therefore the charge is travels in the radial direction, and I get a thrust coming out in this particular direction. Well, this is all about thrusters, but something which we missed out, and I missed it out very intentionally. We talked in terms of electrical rockets, and electrical rockets we essentially went into the principle of electrostatics, E bar, electromagnetics, B bar, how to generate thrust. But something which was very apparent which we did not do was, supposing I have a gas flow and I use maybe a series of resistances here, I put a resistance coil on the wall, and I pass current through this. Well, I can always heat this chamber, and I could have a regular nozzle. That means I heat the gas using a resistance wire, and these are known as resistojets. But not very practical though, See, all what I do is I heat the gas either by putting a resistance wire in the gas, or I heat the wall using some resistance wire. That's just the same way as we have a geyser at home wherein we heat the water. I heat the gas and the hot gas at Tc, and if I were to admit hydrogen which has a low molecular mass, well, I can get a thrust. This is known as a resistojet. And why a resistojet? I can also use a similar principle. After all, I can create an arc, and what is an arc? In the same chamber, maybe I put something like, I pass a gas into it, a low molecular mass gas, let's say hydrogen, and I now generate an arc over here. I strike an arc, I have a high voltage here, maybe a neutral here, I strike an arc over here, and when the gas flows through the arc, it becomes highly ionized, the arc itself dissociates also, and I have very high temperature, and I could expand this out as a high temperature gas, and this is known as an arc jet. In other words, instead of using resistance for heating, I use electrical arc for heating, and the zone of the arc I show like this, highly non-equilibrium, I have dissociation taking place, I have lot of excited species being formed, and these excited species will reduce the efficiency, but I can get high temperature, and therefore I can get a good thrust also. Therefore, these are arc jet thrusters, but they have some problems because of dissociation and the arc which tends to create electrical disturbances. it has been a problem to use them in space, but it can be used. In fact, when we made the first prototype or a discussion on Indian national satellite, INSAT satellite, we thought we will use ammonia as a gas with an arc and use it to generate thrust. Therefore, to conclude the discussions on electrical rockets, we can say, well, electrical rockets are essentially, we could call them as electrical thrusters, since they generally can be used only for low thrust. It could be something like an resistor jet, use electrical resistance. It could be an arc jet. Then it could also be use the electrostatic principle, in which case it could be an ion thruster. It could also be a derivative of, let us say, I correct the ion thruster, I get stationary plasma thruster or Hall effect thruster. I could have a radio frequency ion thruster and maybe colloidal thruster and so on. I could also use the magnetic principle, namely the Tesla, what I have magnetic field, to create maybe the MPD, magnetoplasma dynamic thruster, or I could also have pulsed plasma thruster, and you could keep on deriving in this. Well, this is all about the electrical thruster. We have looked at the principles of this. In this case it is I square R, which is the heat source. In this arc jet again it is I square R. Though the resistor jet is easy to visualize, arc jet is a little more complicated. How do you get the arc going? Maybe the thruster operates in vacuum. In vacuum I have a gap D between the electrode and the neutral over here, and therefore what is going to happen to me? When it is vacuum, I cannot strike an arc. When I start supplying the gas, the vacuum level comes down, and if the vacuum level drops to a level wherein I get the product of pressure into the distance is a critical value, I get something like a discharge coming, I can heat the gas and I can get a thruster. The product of pressure and distance defines when an electrical arc can be found out, and this is what is known as Paschen's law. Some people make use of this for starting a thruster, others make use of, maybe I mount this in a gear train and I can advance this up and down, I strike an arc at a low distance and then I bring it to equilibrium and still maintain an arc, and therefore this is how an arc jet works. Therefore for us we say, well, electrical thrusters are classified into the following, and we have gone into the mechanisms by which these thrusters function. In the next class what I do is, we will wrap through whatever we have learnt in this course, but we will also see, we tell ourselves, is it possible to get Vg to be infinite? In fact, one of the goals which Robert Goddard set was, he said, why not have Vg at the speed of light such that I get an extremely large value of Vj, but is it really possible, or is there some limitation on Vj which affects the performance? And this is what we will see in the next class, in the next hour, right? Thank you.